Set a slider to 0 and the model repeats itself forever. Crank it up and it writes wild poetry that sounds human. Worse, it lies with total confidence. There is one hidden lever controlling this. It's not magic. It's a mathematical scalpel that warps the probability landscape. That lever is temperature, the mathematical scalpel that warps the probability landscape. We're looking at the softmax math that warps the curve, the sensitivity trap that breaks production, and the rule for testing the sweet spot. Get the setting wrong, and you're stuck between robotic repetition and confident hallucinations. So, how do you control it without breaking production? You probably think temperature is a creativity meter, a simple dial. Turn it up for art, turn it down for safety. That's a trap. Temperature isn't a personality switch. It's a geometric tool that warps the probability distribution. Treating it like a vague knob leads to unpredictable outputs. Many guides reduce temperature to plain English labels. This ignores the science. A setting that works on one model may break another. Architecture changes everything. You need the math. Think of the model's raw scores as a mountain range. Temperature is the weather that changes the terrain. Low temperature creates a sharp, narrow peak. The model is forced to climb the highest summit. High temperature flattens the mountains into a rolling plain. The model wanders anywhere. At 0, the distribution collapses. The model is trapped on the summit. It has no choice. As you increase the value, this spike broadens into a hill. A wider range of tokens can compete. The model gains freedom. Eventually, at high values, the distribution flattens toward uniformity. Every token gets equal probability. The model is rolling dice. This reshaping changes everything. A flattened distribution increases rare combinations. It sparks creativity. But it also raises hallucination risk. The mid-range retains a strong peak. It prevents repetition. This is the sweet spot. Temperature doesn't create meaning. It modulates confidence. It shapes the geometry of selection. But the mountain range isn't just a metaphor. It's an equation. Here's the softmax math. Temperature does not add noise. It scales the raw scores before the model picks a word. You are manipulating the denominator in the exponent of the softmax equation. This alters the relationship between the top tokens and the rest. At low settings, you amplify the differences. The softmax function becomes sensitive. The probability concentrates on the top candidates. The model commits. It becomes predictable, safe. Conversely, raising the temperature shrinks the gaps. The exponential function treats scores equally. The curve flattens. Lower scoring tokens get a higher chance. This mechanism ensures temperature isn't a simple on-off switch. It's a nuanced control. It reshapes the landscape based on probability geometry. But here's where the math gets weird. The same number behaves differently across models. Architecture and training data change sensitivity. A value of 0.7 might be stable on one model and chaotic on another. That's why you can't just trust the number. You have to know your model. In a second, I'll show you the sensitivity trap that breaks production apps. This brings us to the sensitivity trap. You might assume a small tweak does nothing. Moving from 0.5 to 0.6 changes nothing. Wrong. Some models are highly sensitive. That tiny shift can flick the narrative. It can alter the tone. It can break the response. Other models stay stable. This variability is crucial for production. It determines your control granularity. If you ignore this, you risk erratic outputs. You cannot reproduce results. You have to measure variance. Run multiple iterations. Quantify the differences. You run the same prompt 10 times. You watch the variance. You measure the standard deviation of the changes. If the output jumps between topics, the model is unstable at that setting. You need that data point. Use automated metrics or human evaluation. Establishing visibility into sensitivity lets you find the optimal step size. If a model is too sensitive, lock the setting. Use a smaller range. If it's robust, experiment more. Document the sensitivity for key prompts. Predict adjustments. Ensure consistency. And that's not even the strange part. The danger isn't just inconsistency, it's confidence in lies. This brings us to the hallucination trap. A high temperature setting can make hallucinations sound more confident. It adds no factual accuracy. It makes errors more persuasive. This is the hallucination trap. Furthermore, over-optimizing temperature yields diminishing returns. Improving the prompt matters more. Enhancing context matters more. Temperature is a post hoc adjustment. It cannot fix fundamental knowledge flaws. It cannot resolve ambiguity. You have to stop guessing. You have to start measuring. In a second, I'll show you the production rule that saves you from overtuning. Finally, here is the production rule for testing. For facts, code, or data extraction, lock the temperature low. This minimizes variance. It keeps the output focused on probable interpretations. It reduces the chance of deviating into unlikely sequences. For creative writing or brainstorming, raise it. Explore a wider semantic space. The key is to evaluate outputs across a range. Test the same prompt with multiple values. Compare coherence, relevance, and variability. Find the sweet spot. But watch the high end. Values above 1 flatten the distribution so much, the model prioritizes novelty over logic. The selection process becomes dominated by low probability tokens. It loses its mind. The interpretation of values isn't universal. The same number behaves differently. Relying on benchmarks is insufficient. Test your model. The parameter interacts with others. Adjusting one alters the other. You need joint optimization. Adjusting temperature changes how the model responds to system prompts. It shifts the baseline confidence. You might need to tweak the system instruction to compensate. This is joint optimization. You can't tune in isolation. So, how do you avoid wasting time? You stop guessing and start measuring. Test empirically. Find your model's behavior. Balance testing with speed. Temperature is the mathematical scalpel that warps the probability landscape. It is not a creativity dial. It is a control over the geometry of token selection. By understanding the softmax scaling, you see how raw scores transform. By measuring sensitivity, you understand your model's unique behavior. By testing empirically, you validate your choices. You move from guessing to engineering. You get the right blend of precision and diversity. You avoid hallucinations. You treat temperature as a calibrated instrument, not a magic wand. To recap, the softmax math shows temperature scales raw scores to warp the probability curve. It turns spikes into hills and hills into plains. The sensitivity trap warns that small changes cause big shifts. Some models are fragile. You must measure variance to find your safe range. The production rule says to test empirically. Use low values for facts and higher values for creativity. Always avoid the hallucination zone where logic breaks down. This is how you use temperature with intention. Temperature doesn't create meaning. It modulates the confidence of the model's choices. Treat it as a calibrated instrument, not a magic wand. If you want AI tools explained without the hype, subscribe. That is what we do here, daily. We break down the complex mechanics of AI so you can use them with precision. That's the full picture. If this made it click, tap subscribe. There's a new AI explainer here every day. And tap the video on screen to keep going. See you in the next one.